do you think that the thruster is the hardest part of the problem?
Yeah, that's the new technology in this satellite. So
Right.
everything else, like the payload, any optical or sensors that we have on there, communications, that's all kind of, we're trying to do that simply. And the new technology that we're developing is the propulsion system.
Okay. And so what sort of things are you just to sort of give a high, like, talk about that, all that stuff we're ignoring? Is the idea that it's just a small box? Like, how much do you think it weighs?
The entire spacecraft, I'm assuming, will weigh around 30 kilograms.
Okay.
I'm still in progress of doing a trade study to see if maybe a larger size would be more efficient. But the payload I want to carry is at minimum 10 kilograms. So this could be, right now we're assuming it's kind of a black box, just an empty mass, but this could be maybe a scientific payload in the future, like a spectrometer, or it could be something commercial. Like if we do mining, it could just be, whatever material you're mining.
Right. And why this instead of wheels?
Yes, so that was a question lots of people asked, and basically it comes down to the amount of gravity the body has that you're on. So wheels, the speed that you can travel is directly proportional to the friction, and friction is directly proportional to normal force. So normal force, it depends on the gravity of the body. So if you have something small like the moon, or even smaller, an asteroid or other moons, you have to move very slowly to avoid hitting anything.
Avoid hitting anything.
Yes, because your stopping distance is much larger if you're driving on a smaller body.
You're not worried about hitting anything when you're bouncing across the moon?
When I'm hopping, I have a payload system that can detect where to land, and also you input coordinates, so you can input, land in this location that we verified from orbit is safe.
All right. Well, I'm gonna push back a little bit. Your stopping distance is, couldn't you just figure out how far you need to stop if you're driving?
Yes, and I have equations for that here.
But I mean, couldn't you, so you'd have to do trajectory optimization with the regular with any wheeled vehicle.
Yes.
Or sorry, you'd have to do trajectory optimization with a thruster vehicle.
Yes. Yes.
Why couldn't you just do trajectory optimization with a wheeled vehicle to solve that problem?
You can, but the optimization problem means that you have to move very slowly because there's going to be rocks and things in the way, and pits. Whereas so imagine a surface which is rocky and pitty, like the surface of Mars, for example. Now this actually doesn't apply to Mars because Mars has a lot of gravity, but just most people know what Mars looks like. So think of Mars with lots of big rocks and small rocks and some holes, and you can't drive your rover in a straight line without stopping. You have to stop to avoid rocks or swerve to avoid rocks. Now, when you have something with a small body, that amount of time it'll take to stop or to swerve will be much longer.
Gotcha.
So you have to move at a very slow rate of speed because it might take you 20 feet to stop.
Right. So it looks like we have a viewer, Amanda. And so why don't you launch into the full presentation? Okay.
So the Regolith Thruster project is being done here at Cornell. The goal of this proposal is to develop this new propulsion system. This will be done by using in situ resources. So the propulsion system is basically moon rocks, or the regolith dust on the surface of the moon. And by using purely electricity, we can throw it out the back of the rocket and in that way hop on the surface of the moon. So this is the technology that we're focusing on. There's a lot of different mission applications that this could be used for, but for now we're sticking to developing specifically this system.
So I guess, Ryan, you're the only person there right now, so feel free to post questions at any point in time.
Yeah, please.
This should be as interactive as possible.
Mm-hmm. So I can. Okay. So yeah, so I can start answering questions that Kevin and Dan posted on the website. So Kevin asked about why this is better than a simple wheeled rover, and I actually started answering this earlier. I'm not sure if you heard part of the answer, but basically it comes down to friction and stopping distance. So the stopping distance for a rover on a small body is going to be very long because there's so little normal force, which is proportional to friction. And that's the same goes for the swerving distance. And so basically with a rover, this will let you hop over those obstacles that with a rocket, you can hop over these different obstacles that you would see in a rover. You would need this long distance to stop. So this means rovers have to move very slowly, and it really limits how much science you can get done off of a battery charge and even maybe over the duration of the spacecraft. So with this rocket, we can hop around, we can pick exactly where we want to do the science or where we want to transport these materials. And it's a different way of avoiding obstacles, specifically optimized for small bodies where there's little gravity. Now, Dan also had that question, but he was also wondering about how to fuel or refuel the rocket. This is kind of still an open question because, as I said before, the primary focus is to get this propulsion system to work. But we have a few ideas about how this would be done. Right now, we're assuming that this is kind of a commercial application and an astronaut may be there, and an astronaut could scoop up some regolith and put it in a filter and put that into this fuel tank. So both of our fuel tank, you can unscrew them and screw them back on in our two designs. But in the future, we're looking at different, maybe you have a robotic arm attached to the rocket. That would be the easiest, maybe from a mission overview concept. Or maybe you have charging stations somewhere remotely around the planet, and those charging stations could include some kind of a robotic fueling mechanism. But for the scope of this project, we assume that this refueling arm or mechanism has like a 20 micron filter on it, so we can get exactly what particle sizes we want. And I think that should be pretty simple to actually make work. So right now we're just assuming that something fuels it with these 20 micron particles. Cool. Yeah, so feel free to ask any questions you might have. Yep.
All right. So why 20 microns?
So basically, the average particle size for a regolith on the surface of the moon is between 20 to 25 microns. So since that's the average, we went with that for this preliminary design. Also, 20 micron particles or smaller is important for ablation. So there's a paper written in the 60s about sand in turbine engines for jets and that kind of thing, because that happens all the time. You get some tiny little particle of dust or sand in a jet actually, and will it break these propeller blades? So the conclusion of that research was anything 20 microns or smaller would not damage or ablate the surface of the blade. Now, I think that we need to do more investigation to prove that that is the case with regolith, because sand is pretty spherical, but regolith actually has 8 times the surface area of a spherical particle. So it's very sharp and pointy, and that's because there's no alien processes on the lunar surface to kind of make this surface nice and smooth. So, so we're assuming from this research in the 60s that 20 microns won't ablate our impellers, but later down the line, if we prove that this is a viable propulsion system, more investigation should be done to verify that regolith won't ablate the surface of the impeller. And maybe some impeller material selection will become more important there.
So the impeller material selection was one of the major focuses of this review. Is that right?
Yes.
Do you want to go through the other ones as well, so people have a high level idea of the big pointy problems that you're focusing on?
Sure. Yeah. So there's the point of this project is to prove that this propulsion system can get X amount of thrust per mass. So thrust is the mass flow rate times this the velocity of the particle leaving the system. So the first thing I'm worried about is maintaining an even mass flow rate through this propulsion system. So to do this, we're looking first at the fuel delivery system, actually. So the fuel tank needs to be able to...
Can I stop you real quick?
Yes.
So that's one high-level requirement, is steady mass flow rate.
Yep.
What are the others?
The other is some final increasing your final velocity of the particles leaving the impellers.
Okay, so so you want to maximize the particle velocity
Mhm.
while maintaining a constant flow rate.
Yes.
Those are the two big requirements.
Yes.
Okay, wonderful. Now let's delve into the first one, the
Okay.
constant mass flow rate.
Yep. So that's going to be controlled by the fuel tank. So the fuel tank will basically spit particles at this impeller system, and it needs to do that constantly. So we have got a few different ideas. One is basically a flour sifter, you can imagine, and another one is basically a spinning funnel. So it's like this shape, and it spins, and the particles fly out the sides because of centripetal force. The challenge to this is that both of these fuel delivery systems need to be able to work in microgravity. The moon has gravity, but during the hop, you'll see at the peak of the hop, some less gravity force because the trajectory, ballistic trajectory that the particles are part of. And if we want to extend this mission or this propulsion system to any smaller body, we want to be able to make this fuel delivery system work in microgravity. So, so that's the first challenge.
So I can see how the rotating centripetal force extractor would work. How would this flour sifter work in microgravity?
Yeah, there's another part to that. So you basically have a flour sifter, and then on top of this, you have a block of material with a weak spring behind it. The spring basically pushes down on the particles, supplying around a g of force, so that they're directed downwards. And then the reason you have a sifter is because it fluidizes the particles. So you get the particles moving, and you've got something compressing them, and then they'll fall out the bottom. Both of these we're building right now using 3D printing, and we're hoping to test starting this week, actually.
And what about this problem would you like the audience to weigh in on?
Yeah, if you have any better ideas of ways to supply a constant mass flow rate of particles in microgravity, I'm very interested in hearing them. If you think that maybe there's a way to take these two existing designs and make them more consistent or more measurable, that would also be interesting. Right now, we're planning on measuring the mass flow rate with a strain gauge array, and that's about it. So anything.
How would you measure a mass flow rate with a strain gauge?
Right. So if you basically hang the fuel tank from something on the top, as the particles come out of the fuel tank, it will get lighter. And the amount of mass that we're expecting to see is around a kilogram of, that's not right. It's we're expecting to see a few newtons change in that force, basically, when we're in 1G. So here on the Earth, we can test this with the strain gauge. However, if we were to use this system in flight, we wouldn't see a significant change in mass because we don't have that 1G of Earth's gravity pulling down on the particles. So in flight, we don't have a good solution to get telemetry of how much fuel there is in the tank. That's basically done by paper and pen. We put this much fuel in, you can burn for X amount of time. So it's really important while we're on the ground here in our lab environment to get a really good estimation of what the mass flow rate of the system will be.
And what other challenges are there to getting the constant flow besides just this dispensing system?
There's also going to be some structural constraints. So you get more thrust if you direct the particles towards the outer radius of the impeller. And right now we don't have a good way to direct the flow. So that's something with the structural design mostly that we are looking into. And I would love to hear anyone's input for clever ideas of how to do that.
So the problem is that you need sort of a tube system that keeps the mass from clumping up as it's feeding into the impeller. Is that right?
So there's two things. One is definitely the clumping that I haven't mentioned. So that would be bad if we had a jam in the way the fuel is being dispersed. So clumping is something we definitely need to be sure we're avoiding. And I can actually talk more about that, but I'll skip to the second one. And that's kind of what I was saying about directing the particles towards the outer radius of the impeller. That's basically simple kinematics. If you have the particles hit in the middle of the fan blade, around its axis, it won't be getting much change in force. But if you have it hit in the end of the fan blade, you'll see a much higher velocity that it is imparted on. So to optimize the thrust that you get out of this fuel dispersion system, this mass flow, it would be better to direct the particles towards the outside of the impellers. Now, back to the clumping, there's different ways that we can see these particles clump up. One is because we're compressing them with this spring. And so even if the sifter fluidizes them, maybe we could see some kind of clumping there, especially since they're so pointy and jagged and have such a high surface area. And that's going to be kind of a mechanical issue. The other way is from static electricity. So regolith can be very easily charged. So it'll be very important in the final material selection of this fuel tank material and whatever blades we have going through it, that we make sure we don't accidentally impart an electrical charge on this regolith and cause it to clump.
Would that just be a matter of materials?
Yes.
All right. So you're looking for a strong, non-abrading, non-charge inducing material.
Yes, which is especially difficult since we do have stuff rotating, and it could be very easy for these impellers to build up charge from their contact with the wall of whatever this propulsion system ends up looking like structurally.
Gotcha. So those are the major problems with keeping the flow rate constant.
Yes.
Is that right?
Yeah.
So let's go over those again.
So we've got the structural issue of where do you direct these particles. We've got clumping, and that's basically the electrostatic discharge and mechanical clumping due to the regolith being compressed.
And then there's also the issue of what's causing the flow in the first place, right?
Oh, yes.
The mechanism.
Yes, the actual mechanism. If there's any way to optimize that, or so as I said, we've got two ideas for how we're approaching that, but any improvements would be very useful.
Great. And so then you mentioned the second half of this whole problem. That's getting the mass flow.
Yes.
Now you want it to then be sped up as much as possible to get the most thrust.
Right.
Right.
So most of that comes from motor selection, of which motor you're actually using to move these impellers. Now, that's kind of a tricky problem. We want something with very high RPM and enough power to maintain its speed when there's a certain mass flow rate. The mass flow rate we've been using for testing is 0.1 floor kilograms per second. It's very slow, but we need enough, and that's partially due to because regolith is very light. But we need something that can maintain this mass flow rate and spin these impellers, but also do it at a very high RPM. So that's a very specific
You're asking
motor.
for the magical motor that has both high speed and high torque at the same time.
Yes.
Okay.
Yeah.
And have you come up with any options for this?
We have mostly some RC plane options, and unfortunately the RPMs we're getting are much less than half of what initially we were hoping for. But this is also just a prototype now with commercial off-the-shelf available parts. We're saying maybe in a real design later down the line, you'll design a custom motor for this application. For now, we've been looking at some RC plane motors that we're going to purchase that can supply about 50,000 RPM at the power that we're using.
Gotcha. And so are you looking for other options in terms of motors?
Yes. I think Dennis motors in particular could be a good option, but we couldn't figure out a way to purchase those without being licensed dentists. And any other types of motors that spin really fast but still have, high power, any of those would be useful. So something like a drill motor is not useful because that spins very slowly. It's designed to have a lower RPM and very, very high torque. We need something with a pretty high torque, but mostly maximizing the RPM. So any ideas of what motors we could use would be fantastic. So that's the main problem with our impeller system. The other problems are structural. So we haven't looked into how we're supporting these motors, the impellers mounted to them. I'm sure for testing, we're going to build something big and bulky that won't be realistic for what you'd see in flight. So that's a whole other optimization that if anyone has any ideas of how to kind of mount these impellers, so I should also talk about what these impellers look like.
Yeah, that would be great. And what you mean by mounting them?
Yes. So basically, there's going to be two impellers, one on top, one on bottom, and they're going to counter rotate, spin opposite of each other. And the reason we chose two is basically a trade study that we already completed. We tried 1, 2, 3, 4, and you see a benefit of √5 times the thrust per the same amount of mass if you use two counter-rotating impellers versus just one.
What do these impellers look like? They just look like fan blades?
Yes, they look like fan blades, but they're not turned. So they're just a flat fan blade like this along the axis, where there's no like spinning that you see in there's no twisting like you would see in a propeller from an airplane, and that's just due to the fact that there's no gases to compress, so there's no pressure to be gained, differential to be gained from that twisted propeller. So it's actually much simpler than your kind of normal fan blade. So it's just basically a flat piece of angled material. Right now the angles we're using is for the first impeller, it's 45 degrees, and the second impeller, it's around 37.5 degrees.
Why that difference?
That difference comes from when you model, it's just straight kinematics of how to get the maximum thrust out of these two impellers. So I'm going to put up there's actually up on the blog some more details in exactly what equations we used and how we got these two angled differences. But if you plot in MATLAB, basically the thrust along these varying angles of impeller blades from 0 to 90, you see that when the second one is 37, it's actually more ideal.
Is that because after they've hit the first one, the particles are moving, but they're not moving straight down anymore? They're moving at an angle?
Yes.
Is that right?
Yep. So the initial velocity of the particles don't actually really matter because, and with that, the initial way that they're moving, when the particles hit the first blade is moving so much faster than the initial particle velocity, you can basically assume that it's just moving at what the blade, so it'll be like this, a 45-degree angle, and your particle will end up like this because it's so much faster than the initial velocity of the particles. After that, there's going to be a height difference between these two blades, and there's the geometry equations are up on the blog, but from this difference in height, you'll see that 37-degree angle for the second impeller is actually more efficient, just based off of that difference in angle. And so coming out of the rocket, you're not only seeing velocity in the z direction, this direction of flight for the rocket, you're also going to see the particles moving at a slight off-axis velocity, and that's because of the 45-degree angle and the 37-degree angle blades. But it's still the maximum vertical velocity along the rocket's axis.
How are you going to account for that off-axis force?
That off-axis force could act as kind of a spin stabilization for the rocket.
So it'll be off-axis, but it will be all the way in a circle around it.
Yes,
right?
so it'll be off-axis
okay.
in the direction that the impeller blades are moving. So in that circular rotation.
So it won't actually put any bias on.
No, it won't be moving along the radius. It'll be moving perpendicular to it. So it won't be biasing, where the force is moving. It'll be kind of, it'll be acting as if there's a small secondary torque around the spacecraft, where the vector of that torque would be along the axis of the spacecraft is traveling. So if anything, that will help spin stabilize the spacecraft slightly, which is good for maintaining a nice trajectory. It just avoids nutation.
All right, so I realized we went a little bit down a rabbit hole. What we're trying to do here is maximize that speed that they're coming out.
Yes.
And the blade angles, mounting the blades. So
yes.
we got very deep into how the impeller works.
Yes.
I think everybody has a good idea of what the actual impeller blades are. So the question is, how do you mount those spinning blades to a cylindrical structure?
Yes. Yeah, how do you mount these blades so that there's the maximum area for these particles to still reach them? So you can imagine the center of these impeller blades is going to have this motor, and you've got two sets of that. So you need to mount these two motors and these impeller blades, and it needs to be strong enough so that it can maintain this crazy amount of torque that these motors are going to be seeing, these impellers are going to be seeing. But small enough in area so that you don't completely block where the particles want to go through and hit these blades.
Have you done any math on that?
No, not yet.
Okay. And have you looked at comparable things like jet engines or jet engines for having spinning things, and then something like CMGs for very tight, fast spinning, motorized components?
Yeah, so we've looked into it a little bit. Not spent a significant amount of time on it yet. We've looked into basically, like I said before, we're looking into building something that's kind of big and blocky and not something you'd want in flight, just so that we can get a test rig of this set up in terms of like strength. In terms of a CMG, just comparing to CMG it's tough because my understanding is that a lot of CMG design, you're designing the motor. So we're using motors that we've purchased and just using them kind of like a black box. We're not modifying the motors because honestly, it's just too much in depth for the scope of what we have time to work on this year.
And why a design that mounts them directly to the shaft?
That was just to be simple and to avoid. The other thing about regolith is that since it's so sharp and pointy, it tends to tear things up. So we were just trying to minimize the amount of material exposed that the regolith could access and eat away at. That could cause a failure mode of this. So we figured putting the motor right on the fan blades, there's not much space for regolith to get in there and kind of break up some kind of a drivetrain.
Got it. Cool. If there's any audience members out there, feel free to type into the chat window any questions you might have. Happy to answer it.
Yep.
Is there anything else that people should know about the regolith thruster, especially areas of interest?
Yeah, so the other thing I'm interested in hearing about is different mission ideas that you guys have for this type of technology. I'm focused on designing the propulsion system, and I think we've gone into a pretty good amount of detail on how that works. And I'm definitely interested in hearing your input. But other problems we have to solve are more of the mission scope. What kind of payloads would you want to see on this type of a system? Would this be useful for science? Could we throw some of these at Titan or some of these small bodies that are proposing to have landing missions, and could that be useful? How could this be used for today's applications? And the idea people have options about how to refuel it, these kind of things. If anyone has good, clever ideas for how to fix those problems, I'm interested in investigating them.
Very cool. Oh, looks like we have a question. The question is from Ryan. Have you considered thermal issues of using a DC brushless motor in an environment with no air cooling?
Right now, we're assuming that we're building the structure primarily of metal, and we're going to have solar panels on the outside of the structure. So hopefully that's enough conduction to get this heat from the motors away, radiate away from the spacecraft. We definitely have more investigation to do for this thermal design system. I'm sure it'll be difficult.
So thermal design is usually one of the latter stages of spacecraft design,
yes.
Isn't it?
Yep.
Yeah.
Yeah, so that's kind of another subsystem. I'm focusing on just seeing if this propulsion system is viable. If this propulsion system is viable, I need to interrogate more thoroughly different aspects of the spacecraft design, including thermal, structural, that we talked a lot about, communications, and recharging. So something that is nice about all of this heat that the motors generate is if we mount the batteries nearby, maybe we don't need to heat the batteries.
Yeah, because the moon is pretty cold.
It gets, yeah, it's, I think it's a 14-day cycle of pretty cold, pretty warm.
Right. Additionally, there's a lot of work on getting DC motors in a cooling restricted environment just because of CMGs on satellites.
Yes.
Is that right?
Yes. So I'm assuming that this problem has been at least interrogated by smarter people than me out there for previous spacecraft missions. So I believe that we should be able to find some solutions. That isn't like the newest part of this project. Ben, you mentioned other things I wanted to talk about this system, and I've just remembered another one that we've left out, power.
So, that's important.
Yes, this is fairly important. So Ryan already brought up DC motor thermal issues. The other thing about motors is that they require power. So something with such a high RPM and power requirement might require more amperage than our batteries can actually discharge. For now, we're using an RC motor battery, so this isn't a problem for our test system. But in the future, if we design a higher powered motor, it could require a higher discharge of amperage than the batteries can supply. It could require you to maybe charge up an ultracapacitor and discharge that faster from your batteries.
What kind of battery is the DC motor? What kind of battery are you using right now? Like
right now, we're using lithium polymer batteries that you would use in an RC system. So I think we're using 7.4 volt RC batteries right now.
Are there batteries out there right now that can output higher amperages?
Yes, there's, I believe the highest amperage batteries are for cars, lead acid batteries. I believe that's the highest. I could be wrong. But a lead acid battery is pretty heavy. They use those in cars because cars can maintain that, can carry that weight. But in the spacecraft, it'll be pretty tough. So lithium polymers are more efficient for us.
Yeah, so it looks like we got another question. Could one change charge and use this to create even flow of the material for an impeller?
I'm not 100% sure what change charge means.
Is that, can you elaborate on the changing charge question? Change charge. So hold the material on a charge plate and then invert the charge to try to drive it towards the impeller.
So I looked into that actually right at the start of this project, and it's trying to very charged to have a small amounts go into impeller. Yeah, so I believe, I could be wrong, but I believe this means trying to use this idea of statically charging the particles to your advantage to maximize, to get even more thrust out of the system. I looked into some ways to do that, and it's tough. And I don't have time to interrogate them while I'm here doing my master's. But I'd be very interested in hearing if people have some ideas of how that could work.
Right.
So
your preliminary investigation was that it sort of a marginal effect.
Yes, the amount of force you get out of it is pretty small. And the other thing is it's kind of difficult to do. So the things I looked into doing are maybe making the outside cylinder that this impeller system would be in a different material from like the fan blades. So maybe have these impeller fan blades charge up these particles, and then they'll want to go towards the difference charge of the outside of the rocket. But then maybe they could clump there, and maybe that could minimize the effect of this delta charge. So I couldn't see a fantastic way of doing that without getting something really complex that's really mass heavy. But it's definitely something we're interested in.
Very cool.
Yeah.
Well, it's 3:30.
Mm-hmm.
There are any final questions? I'm sure you'd be happy to field them. Yeah, and if there's any follow-up questions, feel free to post them to the blog or comment on the YouTube video. I'll be checking both of those. I will post some more details about the answers to the questions Kevin and Dan asked, so that just some equations to back up what I said about stopping distance and such.
So feel free to ask me some follow-up. I'll be happy to look into it.
Wonderful. Well, Amanda, thank you for your time. And
Thank
you
you.
for your time, listeners, for this experimental open design review. And
Yeah,
this
thanks
is
for tuning
the
in.
Regulus Thruster signing out.
Yeah, thank you.